Welcome back to large-scale machine learning. We are going to move on from doing incremental learning to doing scalable machine learning with DASK, which is basically a distributed form of training using this library called DASK or DASK. So distributed machine learning or scalable machine learning with DASK. So DASK actually provides schedulers to manage the parallelism. The DASK scheduler computes the graph in parallel on many different threads, processors, and machines. So any machine learning pipeline can be divided into a series of tasks that can be arranged in a particular sequence. So this actually basically forms a network or a graph in terms of the computation that it does. So this is also called a computational graph, right? So for the first instance, maybe I would add certain values together, and the other branch will also add certain values together, and these two values are basically multiplied together. For example, one vector with the input values after being transformed is multiplied but with the input the weights of the neural network in order to combine it together to form the output for this particular layer. And then I'm going to repeat the process again with other layers. So this computational graph may be as simple as this, or it may be very complex. Now, when we actually try to execute this in parallel, we are not going to execute each of them step by step because some of them can be grouped together. And in fact, if you try to execute it step by step, it will defeat the attempt to make it parallel, right? So because you will still be having a bottleneck of having to do the computations one by one, and some of the results may not be ready yet. So this process will end up waiting for the other branch to be ready before it can actually move both of them to the next step. So we need to schedule all the different branches and processes very carefully so that we can actually execute each of them in turn without having any particular process end up waiting for another process to complete. So you can see that in this complicated looking diagram, the original task is broken down into subtasks, and then each of the subtasks has to be scheduled into a particular processor, which may be running a sequence of steps. So you can see that in this part here, there are several different branches, and each of them are actually running in parallel at the same time because they do not need to wait for each other. Maybe each of them is a different branch of the tree, and hence we can actually compute the results independently. Or each of them is actually a different hyperparameter that we want to tune. Hence, we can try to use different sets of hyperparameters in each of these branches, and we can run it independently as well. So some problems are what we basically call embarrassingly parallel. Okay, some tasks, they can be easily separated into parallel processes. So it's embarrassingly parallel or perfectly parallel. You can look it up. Uh, it's because these tasks, they are very simple to parallelize. So for one example of this is actually grid search, right? So in grid search, you have a number of hyperparameters to try, and you are basically going to step through each combination of hyperparameters. Now, you do not need to do them one by one. If you have a few processors or a few servers available, you can actually use one server to just run through one set of hyperparameters and use another combination to run through on another server. And both of them can actually execute in parallel. So grid search is one of those embarrassingly parallel tasks, right? You can actually run it completely independent and like a separate branch from each other like this. Another one would be random forest. So in random forest, each of the subsample or backed samples can be that's used to generate one more estimator of the tree can be executed independently because every single estimator is using a separate subsample of the training data. So they are not going to be dependent on each other, and you can basically run that training on each for each estimator on a separate branch, right, on a separate processor in parallel. So this is another basically embarrassingly parallel task. So there are many others, right, like this, okay, by just giving you two very common examples of machine learning tasks that are basically easy to parallelize. And this scheduler that's built into DASK help you to parallelize or spread out the load into multiple processes in a way that doesn't cause them to wait for each other. So whether or not wait for each other, it really depended on their connection, right? So this branch actually can execute independent of the other branch. It's only at this point, this common merging point, at which in which case these two branches must actually generate the output at the same time. Otherwise, this merge branch cannot proceed on its own. So here is the dependency. So by looking at the computational graph, we can actually say that, hey, this particular branch A and branch B, we can actually execute them in parallel because they're not dependent on each other. But branch C is dependent on A and B being completed. So there's no point you try to run this in parallel with A and B, because this part here can only run after the first two branches generate their result. So this is basically what this diagram is trying to show you. You need to be careful when you parallelize, because not everything is independent of each other, and you need to take that into account when you schedule the different processes onto different machines, different threads, and different processes. So in summary, actually DAS works very much like an improved version of the NumPy and Pandas library. So you are basically going to write it in a very similar manner. Write your familiar NumPy, Pandas, and scikit-learn code, and then this will actually generate the task graph, right, the computational graph. And once you pass it through the task, it will schedule the right part of this task graph to be executed on a particular machine, and which parts can be executed in parallel in order to produce the final result. So DAS ML is an extension for the basic DAS library, where we actually have estimators and utilities that are basically created to enable large-scale machine learning. So it builds on DAS. So DAS ML is a separate addition to DAS libraries themselves. So what is actually in DAS would be the DAS array and data frame, which I have explained before. These are actually to support very large data frames. So instead of having one gigantic pandas data frame, we actually chunk it down into several large data frames, which can be worked together using the DAS data frame. So it's actually meant for large data sets, and we chunk it into large groups, and each of these groups will be basically a pandas data frame. And when you actually concatenate everything together, you actually support the entire large data set. So each individual data frame or chunk within the DAS data frame only supports one portion of the data. And DAS also supports DAS clusters, so we can actually spread out the load or the computations into a number of separate machines within the cluster, and hence we spread the load. Okay, so this is actually how we accomplish the distributed machine learning and the distributed computation. And DAS contains that flexible task scheduling, right, to actually execute the tasks so that they don't end up waiting for each other. And that scheduling actually involves some pretty sophisticated algorithm internally. So in short, basically, DAS provides the facility for distributed scikit-learn. So scikit-learn that doesn't run only on one machine, but run on multiple machines. And what this actually addresses is what we didn't actually manage to address in incremental learning and gradient descent, which are meant more for memory-bound problems, where you don't have enough RAM to actually store the data so that you can make it available for training. In this case, our problem is CPU bound. What happens if we need many estimators, or we need many different sets of hyperparameters to tune for? So it will take too long to run all these different combinations on one single processor. So these are what we call CPU bound problems. So distributed scikit-learn is necessary in order for us to spread the load over multiple machines. So number one, DAS provides for cluster computing. So you have a cluster of machines to operate, to actually do the work for you. It provides additional enhancements to NumPy and Pandas so that it can work with very large data sets. So for example, NumPy also has a limitation as to how much can be loaded into RAM at one go. So we are going to use this DAS arrays to help you to manage it. And lastly, so actually DAS makes use of the facilities in NumPy. So it doesn't try to reinvent the wheel. It will try to add on additional features over NumPy which it uses for the arrays, right? But it adds on the additional management feature for large data sets. Same for scikit-learn. Thus, ML doesn't try to re-implement all the scikit-learn algorithms. It will use scikit-learn to provide the algorithms, but it provides a management layer over it so that we can facilitate distributed training or training within a cluster. So here is the single machine version of scikit-learn. So typically, if you want to support, you want to do a support vector regression, you import that particular package. You need to do a grid search, and we are going to do a grid search here over the SVR, and then the param grid basically contains all the different parameters. And in this case, I specify this n underscore jobs parameter as -1, which says that I'm going to try to schedule it to as many parallel machines that I have available. So this n jobs is a key parameter. It's part of what we call the job lib library here. And this is actually a task scheduler. So if you have more CPU resources and you can run several things in parallel, you can actually change this n jobs to a larger number, and the scikit-learn will make use of job library to try to parallelize the task. But it doesn't do any sophisticated scheduling. It just finds whatever is available and sends that particular task to it. So what does is that it depends on this job lib library also to do this division of the task, but it adds on top of it a more sophisticated way of actually spreading the load among multiple machines, being aware of the computation graph that's being used when you do that particular task. And once you want to use the computation graph, basically you call the fit function, right, with this grid search, and then it's basically going to try all the different hyperparameters and find the best estimator or the best hyperparameters using the support vector regressor, and then return that value to you. And this basically, although it's one line, will take a lot of computations, because first of all, it needs to do the fitting for the support vector regressor over the entire data set. That's going to take quite a bit of time. Secondly, it's going to try to do it with different combinations of hyperparameters within the param grid. So if you have 10 or 100 different combinations, it's going to try doing this fitting 100 different times with different combinations of the hyperparameters. So one line, but it's going to take a lot of time. And since we set n jobs to equals to 1 and we only have one single server here, essentially it's just going to run sequentially on one single server. So this will take probably an hour or hours to actually return, depending on how big the data is. So let's take a look at the distributed version of it. So notice that the scikit-learn and the job lib is still there, but now we have more than one computer or cluster computers, and we have what we call the DAS library, which does the spreading of the load after it takes the input from the job lib. So it still depends on job lib, right? It doesn't take over the job lib, but now it adds on some intelligence over it on how to distribute the load over multiple physical machines. So the code actually looks very similar as before. So we import the SVR, we import the grid search, we are going to also call job lib, import the job lib instead of just using the n job lib by itself. And of course, we need to also import the dasml job lib. So calling the grid search, this grid search actually coming from scikit-learn, so it's a standard grid search. SVR also coming from scikit-learn, so the estimators come from scikit-learn. The number of parameter grid that we are going to use is the same one as before. In fact, this line is exactly the same as before. What is different is the next line, right? So with the job lib parallel backend, and this job lib comes from the dasml library, we are going to say that, hey, we are going to use the Dask to try to scatter these parameters across different machines. So it uses a different parallel backend instead of the standard job lib library to try to parallelize the task. It's going to use Dask, taking in the number of jobs input from job lib, then separate out the task. Okay, scatter this x, which is x and y, which is the input features and the target label, right? Scatter these values across the different machines and also call the estimator and fit these two values across the different machines. So depending on the task, there may be different ways to parallelize it. So I guess you can probably imagine in a grid search with a large parameter grid, you don't need to use the same machine to try the same combination of hyperparameters. So what essentially we do when we actually need to parallelize grid search is to send one combination of hyperparameters to the first machine, send the second combination to the second machine, and send the third combination of hyperparameters to the third machine. And each of them, actually each of these, since they're using different hyperparameter sets with the same estimator, they can actually do it in parallel. There's no need for them to actually wait for each other, right? And of course, the data has to be sent separately to each because we have to train with the same data. Remember, this is for CPU bound, so we are not concerned about the data itself taking up too much space, right? We are concerned with the computation taking too long on one single machine. So we will copy out the data, since it's not too large, to each of the machines. And with that, we come to the end of this section. So thank you for your attention.